Hello, everybody. This is Dr. Rhonda Cofelt, and I am with Calhoun Community College, and we're going to be talking today about solutions. And so this is chapter 13 in the Tro book that's pictured here. So in this first part, we're going to identify some differences between the states that describe equilibrium and dissolution, such as unsaturated, saturated, and supersaturated, and talk about the mixtures and what's going on with these intermolecular forces that we described back in chapter 11. So solutions are homogeneous mixtures, that is, that they are the same throughout. It's made up of two or more different chemicals, and it could be composed of different phases like solids and liquids, gases and liquids, gases and gases, whatever. In the solution, they have a solute and a solvent, and the really only difference between that is that the solute is what's there in the smaller amount, and solvent is what's there in the larger amount. Now, we usually think of the solvent is like the water, and the solute is like whatever solid we put in there, and that's fine to think about that, but just remember it doesn't have to be that way. It's all absolutely the minor component is the solute and the major component is the solvent. When we form a solution, it's because there are interactions of the intermolecular forces between the solute and the solvent particles. And we've talked about like dissolves like before, so those particles need to be similar, either both polar or both nonpolar, in order to form a solution. Nature, thank you, has a tendency to spontaneously mix, okay? So in diffusion and that kind of thing. So if you pour something in something else, especially like in a liquid, it's typically going to come to a uniform mixture or homogeneous mixture because that is energetically favored in the reaction. And so I just have a little table here, and you can pause it and come back to it and look at it, but these are just giving you examples of the different types of phases that can be in a solution because they don't have to be just solids and liquids. So we've talked about solubility before, and we're going to talk about it again one last time before you go to Chem 2. When the solute dissolves in the solvent, we say that is soluble. So salt, like table salt, is soluble in water. Bromine, however, is soluble in methylene chloride or benzene or other organic solvents. When a substance does not dissolve in another, we say that it is insoluble. So you're soluble or you're insoluble, just like when we have oil and water. Okay, they are not soluble in each other, so therefore they are insoluble. The solubility of one thing in another depends on the entropy of the mixing. Okay, now we haven't talked about entropy yet. You will if you take Chem 2, but it's like the tendency of nature to become random because that's the lowest energy. And so that's why we tend to mix until we get evenly mixed throughout a solution. And also it depends on what types of intermolecular forces are at work. When the solutions have different concentrations of solutes, they will spontaneously mix until they are all the same again. Okay, so that's a natural phenomenon, diffusion. So the effect of the intermolecular forces, we've talked about intermolecular forces before. You should recall at this point, especially if you just got done with 11 and 12, that you have dispersion forces between nonpolar and polar, but in nonpolar, that's the only one they have. Then you have in polar, you can have dipole-dipole, hydrogen bonding, which is a type of dipole-dipole, and then you could have ionic bonding as in the case of ion-dipole. And so how soluble things are depends on what type of these forces that you have in between the molecules themselves and what they're going to have between the solute and the solvent. Because remember, when you have ethanol, okay, you're going to have if you have a liquid jar of ethanol, you have, you know, tons and tons of ethanol molecules, and they all are attracted to each other, or they wouldn't be together. And then when you put it in something else, we're going to have to see which one is stronger, the attraction between the ethanol molecules or the attraction between the ethanol and the water molecule, if that's what we're putting it into. So the maximum amount of solute that you can dissolve in the solvent is called its solubility, okay? And there's a certain limit for each substance, okay? Gases are always soluble in each other because they're going to just mix, okay? They don't really interact, if you recall. They just mix together, so they're always soluble in each other. Liquids, however, sometimes are, sometimes aren't. If they are, they're called miscible, okay? Liquids in liquids. And oil and water are immiscible because they don't mix. And so if it's miscible and you dump two things in there, you're not going to be able to tell the difference. If it's immiscible and you dump them in there, you're going to have two distinct layers of material, okay? And you'll be able to see that if you look at it. All right, so the solubility of one varies with temperature and pressure as well, okay? Temperature and pressure. Pressure is going to influence our gases solubility. Temperature is going to influence everything's solubility, right? Most of the time it's going to increase it. So like dissolves like. So always remember, you got to have compatible intermolecular forces in order for this to happen. Polar and ionic are going to be soluble in polar solvents. Non-polar in polar. I know I keep saying that over and over again, but I do because it's super, super important. You can't forget it. So ion-dipole in our ionic compounds, as well as our polar solvents, when ions dissolve in water, they become hydrated because the water molecules surround the different types of ions. If they're positive, they just surround them with their negative end pointed to them. If they're a negative ion, then they orient with the positive end of the water. That's what makes water the universal solvent, because it is going to surround them. In older textbooks, we used to call this the sphere of hydration, because it would just absolutely attack it, and once it's the water molecules are all around it, you no longer see the individual particles. All right, and so that is basically our introduction to solutions.